Welcome, AP Stats students, for another exciting day of statistics. Today we're going to look at problem set 12.1. So here's our first problem. In the United States, approximately 900 people die in bicycle accidents each year. One study examined the records of 1,711 bicyclists age 15 or older who were fatally injured in bicycle accidents between 87 and 91 and were tested for alcohol. Of these, 542 tested positive for alcohol. Moral of the story is don't drink and bike, right? All right, letter A, find a 95% confidence interval for P. Follow your inference toolbox. Okay, so the inference toolbox. This is basically our checks, and we should also throw in to define the population of interest, right? All right, this over a bit. All right, one study examined the records. We don't know where the records came from. We'll assume, since it's a study, they used an SRS or a valid, sampling technique. So if not, can invalidate our results. So. Okay. The population needs to be at least 10 times the size of the sample. And clearly it would be, right? People have been bicycling, lots and lots of people in the United States, right? There is our target population, people that bicycle in the United States. So the population of people riding a bicycle is at least. What was our sample size? 1,700. Okay. 17,000. So it is safe to use the standard deviation formula. Okay. Normality. So we're doing a confidence interval. So here we're going to be using p hat. So n times p hat, n times 1 minus p hat. And we've got 542 out of 1711. Okay, and the complement. Okay, oh, sorry, couldn't see that. These are observed counts. They're both well over 10, so it's safe to assume normality. All right, now let's do our confidence interval. So 542 out of 1711 is our statistic. And what is our confidence level? 95%. So 1.96. That's our critical value. That's how many standard deviations we go in both directions of the mean to capture 95% of the data on a normal curve. Okay, and our standard deviation. Okay, so there's our work. Now we'll use our calculator. Okay, this is a 1 proportion z interval. X was 542, N is 1711, and we want a 95% confidence. There we go. So we are 95% confident. The true proportion of, I don't know if I want to say intoxicated of, I'll say, and they're not adults either, so I'll say bike riders involved in accidents with alcohol in their blood is between 0.29 and 0.34, roughly, rounded off. And there we go. All right, letter B. Can you conclude from your statistical analysis of this study that alcohol causes fatal bicycle accidents? Okay, there's that really important word right there, cause. Okay, so for example, anytime they throw that word out there, you got to think back to chapter 5 and go, was this a comparative experiment? The answer here is no, this was not a comparative experiment. This is observational data, so we cannot infer causation. So this observational data, so we may not infer cause. Okay. All right. Next, 12.14, side effects. An experiment on the side effects of pain relievers assigned arthritis patients to one of several over-the-counter pain medications. Of 440 patients who took one brand of pain reliever, 23 suffered some adverse symptom, so side effect. Does the experiment provide strong evidence that fewer than 10% of patients who take this medication have adverse symptoms? Okay, so this one is a significance test. Okay, so our p-hat, 23 out of 440. Our null hypothesis, fewer than 10%. So null hypothesis would be, the proportion is 10%. Alternative, fewer than 10%. Okay. All right, checks. Here's where, for n times p, we're using p, not p hat. or P naught. So 440 times 0.1 is 44. Is that 396? Okay, so now these are expected counts as opposed to observed counts, right? Notice the observed count was only 23, but still. These are both at least 10, so safe to use a normal approximation. Okay, that's the normality. Let's see, where did the data come from? We're going to assume that, since again this is an experiment, that they have randomly assigned their patients to the treatment groups. So we should be safe there. So patients were randomly assigned to treatment groups. So the data should be unbiased. Okay, now we're talking about over-the-counter pain relief. So we have lots of people who are using over-the-counter pain relief medication. So we clearly have a population that's 10 times the size of the sample. Okay, so there we go, checks. Now, confidence interval, or no, sorry, not confidence interval, this is a significance test. So let's get our Z. Again, here's where we're using the 0.1. Okay, work that out. All right, this is a 1 proportion Z test. P naught is 10%. And our sample was 23 out of 440. And we have a less than. So there we go. Our Z is negative 3.34. So that's pretty darn significant right there. Again, remember that's scientific notation right there. So that's 0 point that. Okay, so we have very strong evidence that less than 10% of people experience side effects from this pain medication. adverse symptoms from this medication. Yay, there we go. Okay, next question. Do you go to church? The Gallup poll asked a sample of 1,785 adults, did you yourself happen to attend church or synagogue in the last 7 days? Of the respondents, 750 said yes. Suppose it is not, in fact, true that Gallup sample was an SRS of all American adults. Oh, wait, suppose, I don't know why. Suppose that Gallup sample was an SRS. Okay, so I don't know. Forget the parentheses. It's confusing. All right, letter A, give a 99% confidence interval for the proportion of all adults who attended church or synagogue during the week preceding the poll. Okay, so my p hat, 750 out of 1785. Okay. My checks, since I'm doing a confidence interval, I'm using p hat. And these are the observed counts. So 750 said yes. $1,035 said no. Both of these counts are at least 10, so we can assume normal distribution. Okay. We're supposing that Gallup's poll was an SRS, so that's unbiased data. And there are, what was our target population? Adults, yeah, a lot of those out there. Oh, American adults. There are at least American adults. So it is safe to use our standard deviation formula. Yay, okay. Now let's do our calculation. We're doing a 99% confidence interval. Okay, so our statistic plus or minus our 99% critical Z is right there, 2.576. Multiply that by our standard error. Okay, and work that out. Again, I just kind of show that and then go to the calculator. Say 1 proportion Z interval, 750, 1785, 99%, and there we go. We are 99% confident the true proportion of American adults that attended church in the past week is between 0.39 and 0.45. There we go. Oh yeah, confidence interval. All right, B, do the results provide good evidence that less than half the population? Okay, yes. Okay, remember this is a different standard error formula, but 45% is a long way from 50%, and that's the upper bound, so yes. And that's a 99% confidence interval too. Okay. All right, letter C. How large a sample would be required to obtain a margin of error of 0.01 in a 99% confidence interval? Use the conservative guess. Okay, so let's do it. So we're doing 99%. And we're going to use the conservative guess of 0.5. And we need it to be 0.01. Okay, so solving this. Okay, and then we got to do 0.25 divided by that. Looks like we need 377. Did I miscalculate somewhere in there? Double check that calculation. Oh, yes, I did. I divide. 0.01 divided by 2.576. I hit the multiplication button by accident there. All right, square that. There we go. I was gonna say that's more reasonable. So 16,590. Okay. All right. Next problem. Stolen Harleys, Harley-Davidson motorcycles, make up 14% of all motorcycles registered in the United States. In 1995, 9,224 motorcycles were reported stolen. 2,490 of these were Harleys. We can think of motorcycles stolen in 1995 as an SRS of motorcycles stolen in recent years. Okay, A, if Harleys make up 14% of motorcycles stolen, what would be the sampling distribution of the proportion of Harleys in a sample of 9,224 stolen motorcycles? All right. Okay. So the mean would be N times P. So that would be the mean of the distribution is 0.14, right? That's P. And let's see, we got to get our standard deviation. And our our sample size was 9,224. Okay. Oh, and normality, because both counts are well over 10, right? So normal. Okay, so there's our distribution. All right, letter B, is the proportion of Harleys among stolen bikes significantly higher than their share of all motorcycles? All right, so significance test time. Null hypothesis, well, they should be 14% of the stolen bikes, since they make up 14% of all bikes. Alternative, they said, is it higher than that? Okay. Kind of skipping the checks because we said this back here. I didn't write why, but it's because the counts of 0.14 times that and the complement times the 9,224 are both well over 10. So we're good. All right, so let's get our Z. Oh, we need our P hat. Didn't write that down yet. P hat was 2,490 out of 9,224. Okay, so get our Z. There we go. This is a one proportion Z test. Null hypothesis is 0.14. We observed 2,490 out of 9,224, and we are doing a greater than. Wow, look at that Z score. That is huge. Okay, and I don't think I miscalculated. Let me check. No, that's what the answer book also has. So almost 36. So that's basically zero, right? That probability is teeny tiny, 36 standard deviations away. So we have extremely strong evidence that Harleys are more likely to be stolen. Probably because they're more valuable, right? Thieves are probably going to target the more valuable motorcycles. Okay, next question. Coffee. One sample procedures for proportions, like those for means, are used to analyze data from matched pairs. Okay, here's an example. 50 subjects. They're going to taste 2 unmarked cups of coffee and say which he or she prefers. 1 cup in each pair contains instant, the other fresh brewed. 31 of the subjects prefer the fresh brewed. Take P to be the proportion of population who prefer fresh brewed in a blind tasting. All right, so here we go. Letter A. Test the claim that a majority of people prefer the taste of fresh brewed coffee. Okay, and use a 5% level. All right, so here we go. What was our P hat? 31 out of 50. Okay, and the claim is majority, so alternative, the majority. normality checks. Okay, both expected counts are at least 10, so we can assume normality. Okay, as far as I assume we're talking about just adults who drink coffee. Let's see. Yeah, so we have plenty of clearance of our sample to our population, so there are at least 500 coffee drinkers. So it is safe to use the standard deviation formula. Okay, and then lastly, since it was a blind tasting, we should be safe as far as bias. So since blind taste test was used, the data should be unbiased. As long as the coffee was presented in random order, right? If they always presented one coffee first, that could bias the results. So I'll put that in parentheses. As long as the coffee was presented in a random order, right? Because you might end up that the first one that they taste is preferable, or maybe it's the second one. I don't know. I'm not even a coffee drinker, so don't know for sure if it would matter, but it could. All right, time for our test at a 5% significance level. Okay. So 31 out of 50 minus 0.5 over 0.5, 1 minus 0.5, and 50. Okay, so there's our Z. Another one proportion Z test. P naught is 0.5, 31, 50, and greater than. There's our Z, about 1.7. And we get a probability just under 5%. So yeah, this is significant at the 5% level. With a p-value of 0.04, we have evidence that coffee drinkers prefer fresh brewed. At the 5% significance level. Okay. Letter B, find a 90% confidence interval for P. Okay. So the checks change slightly because we have to use our P hat. Other than that, they're the same. So make sure we redo these checks real quick. So 50, and it was 31 out of 50. So both the observed counts are at least 10. So we may use a normal distribution. All right, so statistic was 31 out of 50, plus or minus. We were doing 90% this time. That's 1.645. And again, different standard error here. We're using p hat because we're doing a confidence interval. Okay, so there's our work. And 1 proportion Z interval. Oh, nice, already in there, but confidence should be 90%. Yeah, there we go. So we are 90% confident. The true proportion of coffee drinkers that prefer fresh brewed coffee is between 0.51 and 0.73. Okay, and notice 50% is not in that interval, right? It's close. That's why our p-value was around the 5%, right? But again, keep in mind slightly different standard error. Okay, but they both actually did point to the same conclusion. All right. Oh, there's a letter C over here. When you do an experiment like this, in what order should you present the 2 cups of coffee? I already mentioned that. They need to be presented in a random order to prevent any bias based on order. So. Yeah, it might be interesting to do an experiment where you present them the same exact coffee and see if there's a preference for the first they taste, or if there's a preference for the second they taste, or if it doesn't matter, right? That'd be a fun study to do. All right, 12.18. An automobile manufacturer would like to know what proportion of its customers are not satisfied with the service provided by their local dealer. Customer Relations Department will survey a random sample of customers and compute a 99% confidence interval. From past studies, they believe that this proportion will be about 0.2. Find the sample size needed if the margin of error is to be. Okay, so here's a margin of error calculation, and they're giving me a p to put in. So I'm not going to use the 0.5. In this case, the p star is 0.2. Okay, and what are we doing? A 99%? Right, 2.576. And we need it to be about 0.015. So about, I'll still put in the inequality, right? Could maybe do like approximately, that would have also worked there. All right, solving that. $4,719 is what I get. Okay, part B. When the sample is actually contacted, 10% of the sample say they are not satisfied. What is the margin of error of the 99% confidence interval? Oh, okay, so 10% is not contacted. So we need to redo this with 10% is what they're saying we have to do. Okay. So that would be 2.576, 0.1, 1 minus 0.1. Okay, so reworking that. Looks like about 0.01-ish. Okay. Yeah, that was fun. I like not having to do the checks. Okay, one more problem. A little basketball problem, the old hack-a-shack. Any Los Angeles Lakers fan, right, would know if you were around back when Shaquille O'Neal played, knows about the Shaquille's heel, the free throw shooting of the NBA's most valuable player during the 2000 season. Over his career, Shaq has made 53.3% of his free throws. Shaq worked in the offseason with assistant coach Tex Winter on his free throw shooting technique. During the first 2 games of the next season, Shaq made 26 out of 39 free throws. Now, of course, a lot of people would say, oh, he's improved, but it could be random chance, right? That's the whole point of statistics. So letter A, do these results provide evidence that Shaq has improved his free throw shooting? Follow the inference toolbox. All right, So we're going to talk about our population of interest. So population of interest. Is Shaq's free throw shooting percentage. You know, after the off-season practice. All right, so we're trying to figure out if the practice paid off. Okay, null hypothesis. Nothing's changed, right? He's still Shaquille O'Neal of old, shooting that. Alternative, the practice helped, right? Okay, let's check our normality. I've just been saying P, but those should technically be P naughts, right? All right, how many did he shoot? 39. Okay. 20.787. 18.213. Okay, those are both at least 10, so we can use a normal approximation. All right. As far as free throws in Shaq's career after this, clearly he could shoot 390. So safe to use a standard deviation formula. Okay. Shaq It's like the past, but it's the future. It's kind of weird. Like, what tense should I use here? I'm going to say Shaq took over, or at least 390 free throws. So it is safe to use the standard deviation formula. Yeah. The idea is that this book was brand new and you're doing these problems and you're wondering about the results, but of course this book is now 20 years old, so. Okay, and as far as unbiased data, it should be unbiased, assuming he wasn't injured during this time frame, right? And on top of that, why would an injury make him shoot better? So we can treat these 39 free throws as an SRS of Shaq's season's free throws. Yay, okay, let's do the actual significance test. So we need to know the probability that our Z is greater than, how many did he make out of those 39? 26. There we go. One proportion Z test. P naught is 0.533. We have 26 out of 39 and greater than. So there's our Z, 1.67. 67. So our p-value just under 5%. Okay, so with the p-value of 0.047, I think they did tell me an alpha, didn't they? No, they didn't. So we'll just say we have evidence that he has improved his shooting, free throw shooting. Yay, how fun for Shaquille O'Neal. All right, letter B, describe a type 1 error and a type 2 error in this situation. Okay. So type 1 is alpha, as always. And alpha would be rejecting the null hypothesis when I shouldn't. So this would be concluding Shaq has improved when in reality he has not improved. Okay. Type 2 error would be concluding Shaq has not improved when in reality he has. Okay. Now, these errors, grading tests, students will write a miscalculation. No, type 1 error, type 2 error, these are not due to miscalculation. Okay, these are due to random chance. You just randomly landed on the extreme tail of one of the distributions, and so you're making the wrong conclusion due to random chance, not due to miscalculation. Okay? Letter C, suppose that Shaq has actually improved his free throw shooting percentage to 60%. What's the probability you will correctly reject the claim using a 5% significance level? Okay, so we need to figure out the cutoffs for accepting or rejecting, right? Or the cutoff, because it's a single cutoff here, right? All right, so we're using a H naught was alternative was greater than. Alpha is 0.05. Okay, so sample size was 39. Okay. So we need to figure out the proportion that would trigger us to reject or not reject. Okay. So with a 5% alpha, one-sided, oops, inverse norm, so 0.95, there's my Z. Okay, so 1.645. Oh, I guess I didn't really need that. Parenthesis there. Okay, now we got to solve this to figure out what p hat will be the cutoff for accepting or rejecting. So let's see. Looks like we should get 0.6644. Okay. Now, what are the chances of landing there if 60% is his new free throw percentage? Okay, so we now have to get our z-score. So there's my p hat. Working this out, hopefully we get a z of 0.821. Okay, and a p-value for that is right there, about 20.58. No, that's the greater than. Oh, percent. Okay, that's really not a real strong answer, right? So, and it's due to that sample size and a fairly large standard deviation. So in other words, maybe he has not improved or had, you know, there's just hard to tell with this sample size. So don't jump on board too soon with Tex Winter's free throw shooting clinic. Letter D, find the probability of a type 1 error and a type 2 error. Okay, well, type 1 is alpha, which is 5%. Okay, type 2 is the complement of our power. Oops. Again, I'm putting parentheses because I'm used to writing a parenthesis after that. So that is So again, probability of the type 2 error is massive. So we can't just say, oh yeah, this actually worked. Great job, Tex. We need a larger sample size before we really start analyzing this and jumping to any conclusions. All right, there you go. Hopefully that was fun and informative. Thanks for watching.